Our last theorem of the course is the maximum modulus theorem. Maximum modulus theorem says suppose f is analytic and non-constant on a closed region R bounded by a simple closed curve. Then the modulus of f of z attains its maximum rather, on C. All right, so the maximum modulus theorem says that suppose, for example, your region was a disk. Here's my disk. And C is the boundary curve for that disk. Here's C, and then R is, of course, on the inside. And we have an analytic function on it. And in particular, it's analytic on C. So the derivative exists in a neighborhood of C, so in a slightly larger region. And what it tells us then is it tells us that well, first of all, this is a closed and bounded subset of R2, so it's compact. So the modulum of f is continuous, so it has a maximum. But it happens on the boundary. It doesn't happen inside of R. It happens on the boundary of R. It happens on the bounding curve. So that's what the maximum modulus theorem says. And I would like to give you not a proof of this. It's not done in the book, but in the idea. Well, you suppose not, of course. F of z attains its maximum inside C. Right, so you have some A interior to C, so interior to the region itself, because the boundary of the region is C. So let's say it happens at A, which is in R minus C, so inside. So in our picture here, we have some A, and this is where it happens. What we're going to do is, since it's interior to the region, there's a small ball of some radius that contains A. So let me magnify that a little bit. So here we have A, and here we have a small ball that contains A. And the region is, of course, still here. But we have a ball that contains it. So the claim is that f of A is bigger than or equal to f of z for all z and r. Right? That's it saying. The maximum happens inside. And the idea is that it's possible to sweep out and test a bunch of points around A. So what you do is you look at some r and some theta, and you sweep out a bunch of points in a disk around A. And you do some analysis of the size of these guys. So you can compute the modulus and compare that to the size of f of A using Cauchy integral formula stuff. Okay. In particular, the size of f of A itself is given by the Cauchy integral formula over some circle containing A of f of z over dz over z minus A. And this is like 1 over 2 pi I times integral from 0 to 2 pi f of re to the I theta plus A over re to the I theta, I re to the I theta d theta, and these cancel, and you get something like 1 over 2 pi I integral 0 to 2 pi f of r e to the I theta plus a times I. Okay, and then you do some analysis on sort of appropriately picking the r and theta with that we're not going to go into, and you can show that that you can find actually when you do this sweeping with the r and the theta, you can find a point of slightly bigger modulus. So plus some more serious work. Gives a contradiction. So it gives you another value that has slightly bigger modulus. So what must we have contradicted? We've contradicted that the maximum does not happen on the boundary. So what makes this work is, since we're not on the boundary, we can actually find a neighborhood of A that's entirely within the region. And then once we have that, we can sort of sweep out and find something of bigger modulus. This is also related to Liouville's theorem. So Liouville's theorem says, again, that if you're bounded and entire, so on all of C, analytic on all of C, then you have to grow without bound as Z gets bigger and bigger. So if, in particular, if you're bounded, you must be constant. So if you're non-constant, the only way for this to work is if you grow as you go further and further away. And so the proof of this theorem is kind of in that spirit. You show that there's a direction to go away. So, presumably, if A is the origin, you're going further and further away from the origin, so that the size of the function grows. So it's somewhat related to the proof of that. And again, the proof is beyond the scope of this class, but it's not too hard, and I encourage you to ask me about it or look it up.